Hello friends, the topic is minimum spanning tree. In this video we are going to learn what is a minimum spanning tree, and we are going to learn an algorithm called as Kruskal's to implement minimum spanning tree. So let's start with an example, a real world example. Let's say you are working on an electronic project and you are supposed to make a circuit. So you know that in a circuit there are 6 pins, let's say A, B, C, D, E and F as shown here. There are 6 pins. You are supposed to interconnect all of them with wire. Whenever I am telling connecting, it's all about you need to touch all the pins exactly once, not more than that. Like let's say I touch A and C are already touched, connected. So this is connected, this is connected. So no need to connect C and B because they are already connected here. Connected, connected. So now all the pins are connected, right? So this is what I want. Now in this case, if you observe closely, if you have 6 number of pins, like in this example, you exactly need 1, 2, 3, 4, 5 wires. So if you have n number of pins, you would be needing n minus 1 wires to exactly interconnect all of them. But now the question is, what is the least amount of wire needed? Because there are so many possibilities. This is one of the possibilities. There are so many possibilities. The question is, I need, so like here you see, if you connect A and C, you need 5 meters of wire. If you connect C and F, you need 2 meters of wire. So I need to use as minimum wire as I can. That's the equation. So there can be many possibilities, like in this example, if I connect AC, CF, FE, DE and BD, all of them are interconnected, right? So in this case, the cost, the total cost of the wire in terms of length, this is in terms of length, in terms of meters, is 5 meters plus 2 meters, 5 plus 2 plus 1 plus 4 plus 6, this is 18 meters. If I choose this setup, I will be needing 18 meters of wire. But if I choose this setup, I connect AC, CF, this is a different setup. All of them are interconnected. If you see, exactly 1, 2, 3, 4, 5 wires are needed. Here also exactly 5 wires are needed. So in this example, 5 plus 2 plus 7 plus 4 plus 6, 5, 2, 7, 4, 6, 24 meters is needed. So out of these two, obviously I will go for 18 because 18 is smaller than 24. But wait, there is one more setup. So in this setup, you have, if you connect AB, AC, CF, FE and DE, so the total cost, the length of the wire is 15 meters, which is the lowest out of all these 3. So I think I will go for this connection. So finding this kind of a setup, this is nothing but a minimum spanning tree. Okay. So first let's understand what is a spanning tree. So if you look at this diagram, you can consider this diagram as a graph. Okay. A graph will have edges, these are the edges, and the vertices. So you have one, these are the pins are the vertices, and the interconnection between the pins are the edges. Spanning tree is a tree of this graph which touches all the pin exactly once. Okay. So this is a spanning tree, this is a spanning tree, there are 3 spanning trees I have drawn in this example here. There can be more. So all of these are spanning tree because it spans through all the vertices in a graph. Okay. It interconnects all the vertices in a graph. So therefore it's a spanning tree. Now what is a minimum spanning tree is very simple. Whenever I say minimum spanning tree, it's a minimum cost spanning tree. Okay. So here the minimum cost is 15 meters. So in this example, this is the minimum spanning tree. All of them are spanning tree, and this one is the minimum spanning tree because the cost is minimum. Okay. So let's try to do some formal definition. If given a graph G, where V is a set of vertices and E is a set of edges in that graph. Okay. Now what is a spanning tree is nothing but it's a subgraph of G, or it's a tree. Spanning tree is nothing but a tree. So tree is always an acyclic graph, or it's an acyclic graph. There is no cycle. You remember there is no cycle in a tree. So that's how tree is different from a graph. So spanning tree is a cyclic graph or a tree that connects or touches all the vertices exactly once, like we have seen in the example. That is a spanning tree. Okay. Now, if you have v number of vertices or n number of vertices, we will be having exactly v minus 1 or n minus 1 number of edges in a spanning tree. Like in this example, there are exactly 5 edges in a spanning tree because number of vertices was 6. And what is a minimum spanning tree or minimum cost spanning? It's always good to tell minimum cost spanning tree, MS tree. Okay, is a spanning tree with the smallest cost. Okay, here cost in our example was the length of wire. It can be different thing for a different scenario, length of the wire. Okay. Now, our job is to find out the minimum spanning tree, and as I have told you, there are basically two important algorithms, Prim's and Kruskal's. In this video, we are going to talk about Kruskal's algorithm to find out the minimum spanning tree. Okay. So, Kruskal's algorithm was invented way back in 1956 by Joseph Kruskal. Okay. Now, I will explain the idea behind the Kruskal's algorithm. It is very simple. The first thing is you have to sort all the edges in increasing order of weight. Okay. Sort in a increasing order of weight. Okay. And from that sorted list, you have to select the edge UB, okay, and put it in the minimum spanning tree only if there is no cycle. If it does not create a cycle, then you select the edge. Okay. If it creates, if by selecting UB, if it creates a cycle, you have to skip that edge. This is the idea. Okay. And we say that Kruskal is a greedy algorithm because you are always becoming greedy in a way that you are only choosing the edge with the minimum cost. Okay. You are always choosing the edge with a minimum cost because you would like to finally you would like to find out the tree with the minimum cost. Therefore, it is a greedy algorithm. Okay. This is just an idea, we are going to see it in details. So, let's try to understand the working of Kruskal's by taking this example. Let us say this graph is given to you. Okay. Now, in this graph, let us say these are the cities, 1, 2, these vertices are the cities, let us say, okay, cities, and these are the roads interconnecting the cities. So, city 1 and city 4 is connected directly with a, let us say, 5 kilometer long road, okay, and similarly 3 and 4 is directly connected with 5 kilometer long road. Now, let us say and there is a flood now, there is a flood in a entire country. Okay. So, everything is washed out, all the roads are washed out. Now, your job is to revamp this, your job is to rebuild the roads, okay, and you do not have sufficient fund with you, So, you would like to build a road map connecting all the cities exactly once, but the total cost, a total number of kilometers should be less because the cost per kilometer, construction cost per kilometer is pretty high. So, you would like to interconnect all the cities, but with the minimum length road. So, that's the idea of finding the minimum spanning tree. Okay. So, let us say this problem is given to you. So, first thing I have told you is sort the edges in increasing order of weight. So, this is what I have done in the table. If you see 1 3, this is the 1 kilometer length, okay, smallest cost 1 3, I am sorted it 1 3 and then 4 6 and then 2 5 and then so on. So, it is sorted in increasing order. Number 1 is done. Number 2, you have to select the edge UB in a minimum spanning tree if there is no cycle. You know what is a cycle, right? So, if these 4 vertices are there, if I connect this, now there is no cycle, but if I connect this, again there is no cycle, but if I connect, now there is a cycle. So, if it forms a cycle, you have to skip, otherwise you select it. So, first let us choose the first edge 1 3. So, if I select 1 3, there is no cycle created, so I select it. I select 1 3. Yes, I select 1 3. Done, because it does not create a cycle. Let's move to the next one. Next is 4 6. If I select 4 6, if I choose to construct this road, it does not create a cycle and it is a minimum cost after 1. So, I choose 4 6, no cycle created. Okay. Next is 2 5. If I select 2 5, it does not create a cycle. Okay. So, all the selected edges are marked in blue. Okay. 2 5 I select because it does not create a cycle. Similarly, 3 6 I select because it does not create a cycle. So, I select 3 6 also. What about 1 4? If I select 1 4, it creates a cycle, because if you look at this, 1 is already being touched by this edge, 4 is already being touched by this edge. So, if I select 1 4, it would be the rework, because already a roadway is built from 1 to 4. This is the path. Okay. So, because it is creating a cycle here, if you see, this is a cycle. So, I do not select 1 4. So, I do not select 1 4. Next, 2 3. So, if I select, so if it is not selected, I am marking it in red color. 2 3, do I select 2 3? If I select 2 3, yes, it does not create any cycle. So, I select 2 3. Next is 3 4. Do I select 3 4? No, because they are already interconnected. This is the path. So, I do not select 3 4, because if I select this, it creates a cycle here. So, I do not select 3 4. The next one in the sequence is 3 5. Do I select 3 5? No, because I have already interconnected this, because if I select this, it will make a cycle here. I do not select. What about 1 2? Again 1 2 I do not select, because 1 and 2 are already interconnected via this path. So, it will create a cycle if I select 1 2. Skip. Similarly, 3 6, sorry, this is not 3 6, this is not 3 6, this is actually 5 6, this is 5 6. Okay. I do not select 5 6, because if I select this, it will create a cycle. Please make a note, this is 5 6 and not 3 6. Okay. So, finally, I will get a tree. So, this is a tree, there is no cycle. Okay. All the blue ones, and this is a minimum spanning tree or minimum cost spanning tree, and the length is 15 kilometers. So, I just need 15 kilometers of construction work. Okay, and this is the minimum. This is the minimum. All right. So, your job is to find out a minimum spanning tree like this from this one. Okay. Now, let us see how to implement this, how to write a program to implement Kruskal's algorithm. Okay. If you look at this, the most important thing is to decide if there is a cycle, right. So, you should know how to detect if there is a cycle in an undirected graph, how to detect a cycle. If you know this, implementing Kruskal is very easy. Okay. So, to do this best, there are many ways, but union find data structure can be used to determine a cycle in a graph. So, now I am going to explain you how union find data structure works, so that you can easily detect a cycle in a graph. Okay. So, in a union find, as the name suggests, you have, first thing is you will create something called as a set. It is also called as a disjoint set data structure. Okay. Also called as disjoint set data structure. So, you will have a set of objects. So, in this case, initially you will have set of vertices. So, if this graph is given, there is a function called as a make set. If there are n number of vertices, you will make n unique sets. Okay. So, in each set, a unique element, the vertex itself will be available in that set. So, there are 1, 2, 3, 4, 6 sets created, set number 1, set number 2, set 3, 4, 5, 6. Okay. So, make set will create 6 unique sets. Now, there is one more function you are going to define, find x. if I'm going to define find x, so it will find in which set does the vertex x belong to. So find x will return in which in which set does x belong to. Union UB will nothing do but it will do nothing but merge the vertices UV in the same set. So if U and V are in a different set, if you apply union, now they will be in the same set. Okay. So first thing first, what you do is, given a graph G, you apply make set on all the vertices of the graph. So you will get a set with 6 unique sets like 1, 2, 3, 4, 5, 6. Okay, now this is 5, 6. Okay, everywhere please make this note. This is 5, 6. Now what you do is, obviously you sort all the edges like this. The edges are sorted here in increasing order of weights. Okay. Now first thing first, you have 6 sets in total. Okay. Now if you select 1, 3, okay, how do you know that if there is no cycle? So what you do is, first you find, so there are 2 vertices 1 and 3. Okay. So first find, you apply this function find 1. So where does 1 belong to? 1 belongs to set 1. Okay. Where does 3 belongs to? 3 belongs to set 3. So they are in a different set. So if they are in a different set, what you have to do is, you have to union and make them in a same set. So now they are in a different set. So now I need to join them and make them in a same set. So I have done here. If I do union 1, 3, I have created a blue set wherein 1 and 3 are put together in the same set. So 1 and 3 are in the same set, right? And for implementation purpose, I'll make 1 as a parent of 3. Okay, I could have also made 3 as a parent of 1. Now I made 1 as a parent of 3. So now initially I had 6 sets. Once I do union 1, 3, I will get 5 sets. This is blue set 2, 4, 5 and 6. Let's move on. So the next in the sequence, this is 5, 6. The next in the sequence is 4, 6. So regarding 4, 6, 4 and 6 are in a different set. Yes. So I need to union 4 and 6. If I union 4 and 6, I'll put 4 and 6 in the same set. So this is a green set. 1 and 3 already in a blue set. Similarly with 2 and 5, 2, 5, 2 belongs to a different set, 5 belongs to a different set. So I union them. So 2, 5 comes in a same set called as a red set. So now I have 3 sets in total: red set, blue set and green set. Okay. Now we'll see how cycle is detected. Now the next one is 3, 6. Okay, this is 5, 6. The next one is 3, 6. Let's find out where does 3 belongs to. Let's find where 3 belongs to. So 3 belongs to set 1 or blue set. Okay. Where does 6 belongs to? So let's apply find 6. Where does 6 belongs to? So 6 belongs to green set. So they are in a different set. So if they are in a different set, I need to union this. So I need to put all this in a same set. Okay. So I'll make 4 point to 1. Okay, I'll do something like this. So now for representation purpose, I'll make this entire thing as a blue set, this as a red set. So in a blue set, previously there was 1, 3. Now 4, 6 also join in a blue set. Okay, and let's say 1 is a parent of all the vertices in a blue set. Similarly, 2 is a parent of all the vertices in a red set. So I have 2 sets as of now. Okay. Okay. Now let's see. Next is 1, 4. Now there is a cycle. Let's see how it is detected. Now let's do find 1. If I do find 1, 1 is available in this set, blue set. Where is 4 available? Also in blue set. So if both of them are in the same set, then we say that there is a cycle. Okay. So 1 and 3 are in the same set. So there is a cycle. So I can skip 1, 6, 1, 4, sorry. Very simple. Okay. Next 2, 3. So find 2, and find 3. So, first I will find where it is. So, as of now I have 2 sets with me. Okay. So, find 2, 2 belongs to this set, find 3, 3 belongs to this set. So, they are in a different set. So, let me try to merge them and put it in the same set. Arbitrarily I will choose blue set. Okay. So, 2 5 is interconnected here. So, 2 5 is interconnected here with 1. Okay. So, all the sets, all the nodes now belong to a single set, that is a blue set. Okay. Now, let us see. Now, let us talk about 3 4. Okay. What is 3 4? 3 belongs to the same set. So, 1 represents this entire set, this is a blue set. So, 3 belongs to the same set, 4 belongs to the same set, right. So, I ignore because they are in the same set. So, I skip 3 4. So, 3 4 will create a cycle. Similarly, next is 3 5. 3 belongs to the same set, 5 belongs to the same set. So, a cycle. So, I will skip 3 5. Similarly, 1 2, I will skip 1 2 because both of them in the same set. So, the last one is 5 6. I will ignore 5 6 also. This is 5 6. I will ignore 5 6 because 5 6, both 5 and 6 are in the same set. So, I am done. So, this is how you find, how you implement find and union in union find. So, you can use this for implementing Kruskals. So, this is the final algorithm or the pseudocode for the Kruskal. Okay, let me explain this briefly. So, you are given set of, this is a graph G, W is the set of edges. Okay. Let us say I create a minimum spanning tree, which is an empty set right now, because I am going to select the edges and put it in a minimum spanning tree. This is my this should be my finally, this should be my answer. Okay. So, first thing first, for all the nodes I will have to create a unique set. So, if there are 6 nodes, 6 sets are created. Okay. So, for each vertex V in a graph set of vertices, I will create, Mixit will create a unique set for each node. So, because there are V number of nodes, it will take big O of V time to perform this entire step. Okay. Now, I will need to sort the edges in increasing order by the weight. So, there are E number of edges. So, the best sorting method that we know is n log n. So, E, LG, E. Okay. So, sorting will take E, LG. So, now I have sorted. After sorting, what I do is I will choose A's one by one. So, I will choose a A's UV from a graph. Now, I will see where does U belong to, find set U, in which set U belongs to, and in which set V belongs to. If they do not belong to the same set, if they are in a different set, what do I do? If they are in a different set, vertex U and V belongs to a different set, I will now UB, that A's UB I will add to the MST. So, MST is my set, in that UV is added because they belong to a different set, and then I will union U and V and I will make them put in a same set. Okay. I will repeat this step until I am done with all the edges. Okay. And if they are in a same set, so else part is not there, so it will be skipped, that A's will be skipped, it will not be put in the minimum spanning tree. So, this is how I build up minimum spanning tree. Okay. So, at the end I will return the minimum spanning tree, which is my set of edges that I am selecting for the minimum spanning tree from the graph G. This is the entire idea. Okay. So, this for loop will run E number of times because there are E number of edges. Okay. And if you implement find set and union in a best possible way, it will take log E time to implement it, okay, in a best possible way. Okay. So, E into LGE is E LGE for this entire thing. So, the total time complexity is OV, big O of V for make set, big O of E LGE for sorting, and for the loop for actually doing the find set and union, this is big O of E LGE. Sorry, big O of E LGE, right. So, big O of E LGE. So, if I add them together, this is E LGE is larger than E So B is E LGE. Okay, this is the answer. But I know that E can be number of edges can be less than or equals to the square of vertices, less than or equals to V square. So I can do E LG V square. So this is log property. I can use 2E LG V. Okay, and asymptotically I can write this as E LG V. So E LG V is the time complexity of Kruskal's algorithm. I hope you have understood what is the idea of Kruskal and how to implement it. If you have any doubt, you can comment on this video. Thanks for today.